Hey Physics 2, welcome back to week 3 of class. Today we're just going to be talking about torque and moment of inertia. So here we are back at our table of conversions from linear to rotational motion. Today we're talking about mass and forces conversions. First we want to talk about force. The rotational version of force is called torque, T-O-R-Q-U-E, and to represent it we use a Greek tau, kind of a curvy T. Torque, T-O-R-Q-U-E. Torque, you need to take into account not only the force you apply, but actually how far you are away from the pivot point. The closer you are to the pivot point, the less torque there's going to be, and the harder it is going to be to make something turn. A great example is that it's way easier to open a door or to close it when you pull on the outside rather than when you push on the very inside near the hinges. This is why door handles are on the outside of doors and not on the inside. So back to the table really quick. The way that we convert torque from linear force is kind of interesting. Torque is actually a vector. And it's equal to the radius from your pivot point, the distance you are from the pivot point, times the force you actually apply. But I'm hoping that you guys are going, hold on a second, how do I multiply vectors? I mean, it's one thing to multiply 2 times 4, right, 8. It's really easy to multiply numbers. But vectors have this whole component of direction associated with them. How would I multiply, like, left times up? Well, that's where this comes in. This is a special kind of multiplication for vectors called a cross product. And the cross product takes 2 vectors, you multiply them, and it spits out another vector that's perpendicular to those first 2 vectors. For most of what we need in this class, in fact, I'm going to say for all of what we need, we can actually just say that the amount of torque, ignoring the vector direction, the amount of torque that's produced by a force applied at a radius is going to be the R times the F times sine of the angle between the radius and the force. So let's look just a little bit closer at how that plays out. I'm going to color code this because I think it'd be helpful. Let's say we have a door that we're opening, and here's our vector R. That's from the hinge of the door all the way out to where we're pushing on it. And we're applying a force on the end of the door, force F, where the handle is, like that. These are both vectors. Now, the torque that I'm producing here by pushing on this door is RF times the sine of this angle between R and F. So if I write that out, it looks like this. And this angle can vary quite a lot. You can see sine of, if it's at 90, sine of 90 is going to be 1. So it's just going to be R times F, which is kind of the nicest scenario where we don't really have to worry about some angle in between. If I decide I'm going to open the door really strangely, and I push horizontal, parallel with the door, the amount of torque is going to be a lot less. In fact, R, F, sine of 0, not theta, 0, sine of 0 is 0. So in this case, there's no torque applied. And it's not going to actually rotate in any way. We should also talk about, while we're here, there's another formula used to define torque. It's not a conversion from linear properties. It's actually just pretty much the equivalent of Newton's second law, F equals ma. So remember, F equals ma. The rotational version of that is torque is equal to this new thing we're going to call I instead of m times alpha. We're just substituting in alpha for a. Remember, alpha is the angular acceleration. Well, this new thing I is moment of inertia. So this moment of inertia thing we call I goes into this part of the table. It has units of kilograms times meters squared. And it has a lot of different formulas, which we're going to look at in just a second. There are many different formulas depending on the shape. Mass is related to it, but it's also related to the actual shape and, in fact, where you're rotating from. And you know, while we're here, let's fill in the units for torque, which are Newton meters. A lot of times you'll see for non-metric pound feet, which is just a silly unit. But Newton meters are nice and standard. Here's a pretty typical table showing some examples of moment of inertia for different shapes rotating around different axes. Don't worry, you're not going to need to memorize any of these. On tests and homeworks, I will give you a table just like this. For a hollow hoop rotating about a symmetric axis, it's kind of like a wheel, and this is kind of the simplest moment of inertia. Equals the mass of the hoop times its radius squared. For more complicated things, you can get different ones, like a solid sphere, which is not just like a shell, but like solid all the way through, is 2/5 mr squared, whereas that shell, which is just mass on the outer edge of the sphere, is only 2/3 mr squared. These differences cause huge amounts of difference in the way things roll. And when we get to rolling later on in this unit, we're going to see a couple of awesome experiments that show this really, really nicely. In fact, right now I'm going to recommend that you go and look up a video by the physicist Walter Lewin. He's a great physics teacher from MIT. I'll find it and link it on our classroom website. He does a really wonderful little experiment showing the different moments of inertia and how they affect something rolling down an inclined plane. A great example of the moment of inertia changing is when I'm spinning around here. I'm fairly compact. I'm spinning at this rate, but if I stick my legs out, I'm going to increase my radius and therefore slow myself down. And that's it for this week. Even the cat wants to get out, so I'll see you guys in Zoom. Bye!